So hello everyone, welcome back to my YouTube channel. And today we are going to learn about some interesting topic that is RAG. So before getting started, I will ask you something. Have you ever used ChatGPT or any AI tool and ask him a specific question? Let's say something about your company or about your college or about your own documents. So you must have seen that it either gave you a completely wrong answer or it must have said you, I don't have access to that particular information. So that gap between what you needed and what the AI could give you, that is exactly the problem that RAG solves. So let's get started. Let me tell you a story first. Forget the AI for a moment. Just follow me on this. So let's say, imagine you are a patient basically. Okay. And you're not feeling well. You're tired, you're thirsty, maybe you're a little dizzy. So you go to clinic and you sit down in front of your doctor and you ask him, Doctor, what disease do I have? Now here is the thing, the doctor is brilliant. He has went to one of the best medical college in the country. He has spent many years studying every disease, every symptom, and every treatment protocol. Okay, so the doctor's general knowledge is exceptional basically. But but a particular doctor has never seen your file. The doctor doesn't know your blood test reports. It doesn't have, blood sugar reports or readings, or it doesn't know you, and he doesn't know what is a previous diagnosis and whatever. So basically, the doctor has only the knowledge, but it doesn't know the patient basically, correct? Now, what doctor will give the answer? Now, this will try to understand in analogy, right? Without RAG and with RAG. Now, in this case, without RAG, so doctor may give answers such as maybe you have a diabetes, or maybe you have any chronic disease, or you have thyroid, whatever. So basically, the doctor has not seen your medical report, so doctor is guessing that you may have this particular disease. On the other hand, if the situation is something different, same patient, same doctor, same question, but there is only one single change. So this time, before doctor gives you an answer, there is something called as retriever. Now, what is this retriever? Think of it like now as a hospital assistant whose job is to run the records, whose job is to run to the records room and find your specific medical file and bring it back to the doctor basically. Now, this retriever goes, searches from hundreds of files, and it finds your medical records and brings it back to the doctor. Now, the doctor looks into that file. Now, the doctor knows your medical report, what is your blood sugar, what is HB1 IC value, what is previous diagnosis you have, and whatever reports you have basically. Now the doctor has idea that what previous diagnosis you have, what are your reports and everything. So now doctor will not guess the answer. It will try to give the answer confidently. He will say that you have type 2 diabetes, your blood sugar is this particular level, which is significantly elevated, or your this particular value confirms that you have a chronic high glucose level, whatever it is there. So in this case, doctor had a right information at a right time before he answers. So basically, what is RAG? So RAG gives your AI system a way to go and find the relevant information first and then generate an answer. So before generating an answer, go and find the relevant information, give the information to me, and using that information and whatever knowledge I have, I will generate an answer basically. Okay. So mapping this analogy, what we have learned, so we can map like this. So the doctor is nothing but our LLM. LLM is large language model, and we have already discussed about LLM, overview of LLM in the previous video. If you haven't watched that video, the link is in description. Go there and watch. So now LLM is nothing but the brain, the intelligence, the thing that actually produces the language and answers, correct? So the LLM has vast general knowledge, but it needs a right specific information to give a reliable answer for your use case basically. Now, the medical report here is nothing but our knowledge base. This is your data. So your documents, your PDFs, your databases, or your policies, whatever. So your information basically, the specific information to your domain that no general purpose LLM was ever trained on. Now, the LLM has trained over some particular data, but that particular data is not your personal data. So this knowledge base is nothing but your personal data, your medical reports, your documents, etc. Whatever it is. So this is what makes your AI assistant uniquely yours, basically. Correct? Now, what is finding the report? That is nothing but a retrieval. Retrieval means the process of searching through your knowledge base. So whatever documents I have provided, that is knowledge base, my personal documents. Through that documents, I have to retrieve something. That process is nothing but a retrieval process. Now this particular thing will retrieve, pull out some most relevant pieces of information for a given query. Now here my query was what disease I have. So according to that particular query, it will retrieve some of the important information in relevant pieces of this. And then you have answering the patient. Answering the patient is nothing but generation. Now you have your knowledge base, you have LLM, you have retrieved the particular information. Now it is time to generate the answers. So the LLM takes the retrieved information, it reasons over it, and it generates an accurate or grounded answer basically. This is nothing but the G in the RAG, that is generation. So what is RAG basically? RAG is nothing but first, R is retrieval. Retrieval means go find the relevant information. A means augmented. Add that particular information to the context window. And G is generation. LLM answers using the context window. Before that, we'll just look why we read RAG. Without RAG and with RAG, what is the difference? Now, to really understand why RAG was invented, we need to understand what breaks when you use an LLM completely on its own without any retrieval system, basically. So if I use without RAG, what is the source of knowledge? Our source of knowledge is LLM itself. Correct, only LLM. So what are the problems for LLM? We have already discussed in the previous video where we discussed about the LLM. Let us discuss it once more. So first thing is about knowledge cutoff. So what do you mean by knowledge cutoff? So basically, every LLM is trained on a massive data set. You already know that. That is billions of web pages, or any books, or any articles, or codes, or repositories, etc. So this particular LLM is trained on a massive data set basically. But this particular training has a cutoff date basically, a fixed point in a time after which the model knows absolutely nothing about the world. Correct. Now, if you think about what this means practically, so let's say if your LLM was trained with date up to early 2024, let's say, and you ask is about something that happened after 2024 or about your company's new policy that was published last month. So basically, that LLM has no idea about this. It has the idea only about that particular data before 2024 and not after 2024. So the particular LLM has zero idea about this. So it will either say, I don't know, or make some guess. Correct? If you talk about some business context, this is a very serious problem, right? So in business, information changes constantly, policies gets updated frequently, prices changes, new products gets launched, regulation changes. So LLM trained even 6 months ago is already a partially out of date basically for a specific domain. So this is nothing but a first problem of LLM, that is knowledge cutoff. Second problem is again fine tuning doesn't scale. Now, some people hear the knowledge cutoff problem and immediately say, okay, fine, just fine tune the model on your own data, give it your documents and retrain it. Fine tuning is a technique. It's generally useful for teaching the model specific style, tone, or format. But it is not the right solution for keeping your AI system up to date with changing information. First thing, it is expensive. So fine tuning a large model costs thousands of dollars, correct? Second thing, it is slow. A fine tuning can run take hours or even days depending upon the model size and the data set. And third thing is it impractical. It doesn't update easily. Every time your data changes, a new policy goes out, a new product is launched, a price gets updated. So you would have to fine tune the model again and again, which is completely impractical. Okay, so think about it in this way. Fine tuning is like sending the doctor back to medical school every time a new patient comes. Correct. So no hospital does that. You train the doctor once properly and then you give them the patient's file at the time of the consultation. That's RAG. Third problem we have in LLM is hallucination. So why this hallucination happens basically? Because the LLMs are trained to predict the next most likely token, the next word basically. So they are optimized to produce coherent, grammatically correct words, right? So when they don't have specific information needed, They don't stop basically. They don't say, I don't know. They just continue producing the most statistically likely continuation of the text. So, and that continuation might be falsy or factually wrong, correct? So the particular LLM is not lying to you. The model doesn't have the intent. It is just doing what it was trained to do. It was trained to predict the next word. So it is doing its own work, correct? So this is one of the biggest problem. And this problem is reduced by using RAG basically. The fourth problem is huge context windows are not enough. So modern LLMs have very large context windows. Some can handle hundreds or thousands of tokens. And people say just paste your entire document set into the prompt basically. So basically here what happens? So let's say imagine your company has 10,000 documents. Each document is of hundreds of pages. So you literally cannot fit all of that into one prompt basically. So volume gets increases, right? Even if you can fit everything, research shows that LLMs don't pay equal attention to all parts of long context. So information in the middle of very long prompts tends to get lost. So this is the problem with the context windows. Correct. So the model pays less attention to it. So flooding the prompt with everything doesn't guarantee you get the best answer. So RAG solves this by being selective. So instead of dumping everything, it finds and sends only that particular relevant pieces. Precision over volume, quality over quantity. So this result is faster and it is also cheaper and it is also accurate. Correct? So with RAG, all four problems are solved. Not 100%, but yes, it gives us better results than LLM. So if you use the latest data, so your knowledge base is separate from the model. You update your documents today, or the system reflects them immediately. So so there is no delay. Also, we don't require any retraining. Then comprehensive search. Comprehensive search means it makes use of something called as semantic searching. It finds the most relevant information from thousands of documents basically, and it finds it instantly based on the meaning and not just the keywords. We'll see about the semantic search in more detail in the further video. Third thing is about the grounded answers. So the LLM answers from real retrieved documents. Hallucination drops here, correct? Because the model is now anchored to the facts and not just the statistical patterns. And the fourth thing is no retraining needed, correct? The model stays the same, only the knowledge base changes. Our model is same, but only our knowledge base changes according to our query or according to the user. Now we'll try to understand in more clear way. Look at this particular diagram. Okay, so without RAG, the first diagram. So when asked about Amazon's return policy, the answer is uncertain. What is the answer? What is the prompt basically? What is the return policy for products on Amazon? So in the history state, it has a e-commerce customer support. LLM is trained on particular data and it is trained up to particular date. So what is the answer given by the LLM? Amazon usually accept returns within 30 days of delivery. Please check the Amazon website for most accurate information. So this is the particular answer. Okay. So that's uncertainty, correct? So this answer is uncertain. Please check the Amazon website for more accurate information. Now, if you see with RAG, what is the return policy? Same question is asked. What is the answer given? Yes, Amazon accepts return within 30 days of delivery for most items. And it is giving something citations like one, some items have extended return window up to 90 days. Two, for more details, visit the official Amazon returns and refund page. Three. Okay. So with RAG, the same question returns are precise, specific, and more importantly, cited answers. Okay. Now here in this case, with the number citation, you can see 1, 2, 3. So there is no uncertainty, just an answer grounded in actual policy document. So this is the difference what RAG makes. Now what is this architecture? You can see a retriever, encoder, vector search, and ranker knowledge base. This we are going to see further in detail in the further video basically. Okay. Now what are the real life applications of RAG? Why it matters basically? Before we build out our technical pipeline, how the RAG architecture and go in further details, first it is very important to understand why we are studying RAG. Does it have any scope or does it have any applications, real world applications? So yes, it has First thing is in education, college bot. So universities have hundreds of documents, student handbooks, exam policies, fee structures, rules and regulations, admission guidelines, courses, and so on. Correct. So these many documents that particular university has of its own. So student asking a question doesn't want to dig through the 12 PDFs. So we can build a college bot. It will directly ask to that particular bot, and that bot will have basically have that particular all documents. So it has a knowledge base basically. So RAG powered college bot can answer any question from all those documents instantly. And also it is accurate, and also it will give us the sources from which particular document I have extracted this particular information. Similarly, in healthcare, where we have to do patient record analysis. So before a doctor enters a consultation room, they can ask the system, summarize the patient's last 6 months of records. Okay. So the RAG system retrieves from hundreds of medical entries and generates a precise structured summary in seconds basically. Third application can be customer support, live product documentation assistant. Okay. So basically companies like Notion or Salesforce or any SaaS product have documentation that changes constantly. So a RAG powered assistant can answer any support question from up-to-date product documents in real time basically. So you must have seen in websites, there is a chatbot at the right corner, customer support. So you ask the questions regarding that particular product or anything about that company or anything about that product. Okay, anything you can ask. Then another application can be in legal tech, contract query platforms. So lawyers also deal with thousands of pages of contracts, regulation, and case laws. So this can be also used in legal tech. So these were some of the applications of RAG. So there are many such applications. You can go and search on the internet for that. Now comes the most important topic. Let's move ahead. That is components of RAG. First component is data sources. So this is a raw material, the starting point of everything. So what is data sources? Basically, it is a collection of all documents, files, information that you want your AI to able to answer from, correct? So it may include your PDF, documents, website, databases, anything. So basically, if you have example of university, so it may include the exam policy document, fee structure document, rules and regulation document, courses document, academic calendar, so on. And this can be in different formats. It can be in PDF, it can be in Excel, it can be a Word document, it can be HTML, whatever. So a real RAG system needs to handle all of this. And the data can be messy also. The data can be inconsistent also. It can be unstructured. So just getting this data ready is the first challenge basically, correct? Second component is retriever. What is retriever? Retriever is a search engine of your RAG system. It is going to basically retrieve the most relevant information. So given a user question, go find the most relevant pieces of information from the knowledge base and bring back them particularly. Okay. So the keyword here it is semantic retrieval. What is semantic retrieval? Semantic means it finds the information based on the meaning and the intent and not just the keyword meaning. It will see the meaning also. So basically it will not match word to word. It will match in the meaning. If the meaning aligns, the retrieval will find it. Third component is knowledge base. So where actually our data will be stored, correct? So this is where we'll process the data. Process data will live. Knowledge base is not a regular database basically. It is something called as vector database. We have already learned about vector database. It stores text converted into numerical representation basically. Correct? Which is called as nothing but a vector. Popular vector databases are nothing but ChromaDB and Pinecone. Okay. We'll go very deep on this later. Fourth component here it is LLM. LLM, that is a generative model which will generate a final answer, right? So it is nothing but an intelligence layer. So it will take the user question and it will also take the retrieved context basically. Question plus context. And it will understand both, generate a accurate natural language answer basically. Fifth component here it is answer and sources. Now this is the final output basically. So a well-designed RAG system will not just give an answer. It will give you the answer with references. So it will return the answer along with reference. It will tell you exactly which document or which page, which which source the information come from. Okay. This is critical for trust and also verifiability. So when a student gets an answer about their exam policy, they should also see like this. This is from the exam policy PDF, page number 5. So now these were components of RAG. Now the RAG pipeline is basically divided into two phases, what you can see here. First phase is nothing but indexing, and second phase is retrieval and generation. Indexing, which also known as a offline phase basically. So offline phase or indexing phase, it's nothing but a preparation phase. It happens before any user ever asks a question. Okay. So you take all your documents, you process them, you convert them into a searchable format, and you store them basically. So the steps are your ingestion, chunking, embedding, storage. So think of it like building a library. So you're not just piling books in a room. You're cataloging every chapter, every paragraph, indexing every concept, and basically organizing everything so it can be found instantly, right? So you do this work once and then the library is ready. And the phase two is nothing but retrieval and generation. This is what happens every time a user asks a question. So this is a real-time phase or an online phase. So whenever a user asks a question, this particular phase will run. The system retrieves the relevant information from the prepared index basically, and it will generate the answer. So these are the complete overview about what is phase one and phase two basically. Now, what is the reason that these phases are completely separate? That is the performance. If you have to process documents every time a query come in, the system will be slow basically. So phase one is done once, that is offline phase. And phase two is fast because all the heavy lifting is already done. The heavy lifting is just preparation of documents. It is already done in the phase one, and phase two becomes fast because this is already done. Now phase two is only in phase two, we only want to retrieve the particular documents or information and generate the answers. Correct. Now let us try to go in more detail in this particular two phases. Okay. So we are going to take an example, and with that particular example, we are going to understand all this particular step-by-step pipeline basically. So the example is AI assistant for university. The first phase is indexing. In that, the first thing is ingestion. What is ingestion? Ingestion is process of loading your raw documents into the system, then extracting the text, cleaning the text, standardizing the format, and storing that particular documents in a format basically. Okay. So the flow is something like this: load the documents, extract the text, clean the text, standardize the format, and store the raw documents. Okay. Now let's go step by step. Loading of documents. So loading of documents means you feed the system your source files. In our university case, that means of PDFs like student handbook, exam policy, Excel files or fee structure, Word documents of the hostel rules or academic calendar or website, whatever. And here also we support different file formats: PDF, Excel, document, website, HTML, whatever. Okay. Extracting the text. So once you load a file, you extract the raw text. So from a PDF, you pull the text layer. From an Excel file, you convert the and structure into readable text basically. From a web page, you strip the HTML tags and get the just the content basically. So this is nothing but the extracting of text from different sources. So this sounds simple, but it is very complicated or tricky. PDF with scanned images where the text isn't actually a text, it's a pixels. So for that, we need something called as OCR. PDF with complex tables layouts need spatial handling. Then can be content which have different languages, multilingual languages, correct? So it needs the right character encoding. So these edge cases are where a lot of RAG systems encounter their first real challenges. So first very important challenge is about the extracting the data. So you have documents, but the extracting the information is very important. So once you've extracted that, the next biggest challenge is cleaning that information. It is not that always the information you get is structured and in a format. You should clean that text. You should standardize the format basically, like removing the extra spaces or special characters, removing the header footer, or removing normalizing the encoding or standardizing the format basically. Correct? After cleaning, what happens? Every document gets into a consistent structure, typically a plain text with metadata attached. Now, this metadata is nothing but the information about the documents, like its name, its type, its source URL, or file path, when it is created, which department it belongs to, what is the version of the document. Now, this metadata is very important because later when we retrieve this particular data while searching, metadata can be used to filter the results. For example, only search fee related documents or only show documents from last 6 months. So without metadata, you can't do this kind of filtering. So this metadata is very, very important. Now, what is the output of this ingestion? So this particular ingestion step, whatever things are there, load document, extract, clean, standardize, store raw documents. So the output of ingestion is nothing but a collection of cleaned raw text documents which are ready to be chunked. Now what is chunk? So chunk is nothing but our next step. Step 2, that is chunking. What is chunking? Chunking means, from the word itself, you can understand chunking means cutting down documents into meaningful pieces. Okay. So why we chunk basically? First thing, LLM has limited context window. Correct? So LLM can only process a certain amount of text at once. So that limit is called nothing but a context window. So basically, it is measured in tokens, right? So even modern models with large context window, which can't receive entire documents set in one prompt. So you need to basically cut that particular documents in meaningful pieces, related documents in one chunk, the other related documents in another chunk, so that we can give that LLM the documents in chunks and not the entire bit, basically entire the documents. Correct. Then meaning is preserved, correct? And retrieval is precise and fast. So when you retrieve the information, you want a surface, a focused piece of text that directly address the particular question. So instead of giving an entire 1,000-page document, we can give it in chunks, that is in meaningful pieces. So according to the user query, that particular related document will give him so that the retrieval become fast and precise. Okay. So this will make the performance also better and accuracy also will be better. Now, what are the different strategies of chunking? How we can cut these particular documents in meaningful pieces basically. So the different strategies are fixed style chunking, sentence level chunking, semantic chunking, and hierarchical chunking. Let us try to understand them one by one. So first thing is a very simple one, that is fixed size chunking. Okay, so you split your documents into chunks of fixed size, say 80 characters or 500 tokens. So basically, from this particular example, so whatever uh, information I have, that particular information will get break or will get chunk after 80 characters. So example 80 characters. So this particular thing will get chunk after 80 characters. Then next particular thing will chunk after 80 characters. So it will split that particular information in 80, 80, 80 characters like this. Now this particular thing is very easy to implement, very simple to implement. But what is the problem here? Problem is that it will cut the sentences in half, right? It will destroy the context basically. Now here you can see the semester fee must be paid before 30th June 2025. And sec 2.a. Now this particular sentence is cut into half. So this particularly will lose the context. It will lose the context. So basically when we can use this particular fixed size chunking. So we can use only for rapid prototyping or when the context is extremely uniform, but we cannot use it production level applications because this will basically cut the sentence and it will lose the context. Next is sentence level chunking. This is a more smarter approach than fixed level chunking. So instead of cutting a fixed character count, you can cut a sentence boundaries. Let's say at question marks or at full stops or at explanation marks. So each chunk is one or more complete sentence. So the chunk 1 is semester fee must be paid before 30th June. Chunk 2 is a late fee of 500 will be applicable. Chunk 3 student who failed to pay the fee like this. So it is chunking sentence by sentence. Correct. Now here the pros are sentence are intact, much more reliable and meaningful, better retrieval quality. But cons is chunks can vary a lot in size, right? A single one-word sentence and a 50-word sentence become separate chunks, creating an imbalance in the retrieval. Correct. So these are the cons of this particular chunking strategy. So next we have third strategy, that is semantic chunking, which is most widely used. Semantic chunking doesn't split at character or not it split at a sentence boundary. It uses embeddings basically to detect whether the topic or meaning shifts in the next. Think of it of this way, like you read a document, you naturally feel where one idea ends and another begins. So even if there is no split heading or section break, semantic chunking teaches the computer to detect basically that same shift by measuring how much that embedding nothing but the meaning, correct, changes from one sentence to the next sentence. So when there's a big shift in the meaning, that's where the chunk boundary goes. So let's say the topic is fee deadline. So fee deadline is the topic. So my chunk will be the semester fee must be paid before 30th June. Now if the topic is late fee, so here the late fee, related to late fee, whatever is your chunk, that will be stored separately. And what is the consequences? Student who fail to pay the fee within the stipulated time will not be allowed to appear in the exams. This is the consequences. So basically the semantic chunking will split the information based on the meaning of the topic. And for that it makes use of something called as embeddings. Correct? So what is the pros? Pros here it will respect the meaning and it is better retrieval quality. But what is the cons? It is more complex to implement because we require an embedding model here. What is an embedding model? It will see the meaning of the sentences also, and according to that, it will chunk. Okay. The fourth strategy is about the hierarchical or parent-child chunking. So how this particular hierarchical chunking works? So basically, we have here a parent chunk, and the parent chunk consists of larger pieces of text, or you can say complete paragraph or a sections. So they provide a complete context for the LLM to read and understand. Okay. And then we have a child chunks. Now, what these particular child chunks do, these are small, highly specific and atomic pieces derived from that particular parent chunk. So these are used for search because they are precise and focused, and also the matching is more accurate. So if you see here, the parent chunk consists of, this is particular one section. There are three sentences in this particular parent chunk. And using this particular parent chunk, we will create some child chunk. One is semester fee deadline, late fee rupees 500, not allowed in exam. So basically, these child chunks are linked to this particular parent chunk, correct? Now, here is a beautiful part of how it works. So the search is done on the child chunks. So a user query matches against a child one precisely. But what gets retrieved and sent to the LLM is a full parent chunk. So the LLM gets complete context to generate a comprehensive answer. So this is the working of the hierarchical chunking basically. So what is the pros here? It gives the best balance of precision and context. It is great for the production system. But the cons here it requires a more storage. You store both the parent chunk also and the child chunk also. And it also complex to implement and manage also. Correct? So this was all about the chunking basically. So first step was ingestion and second step was chunking, where we cut that particular documents into meaningful pieces. So third step here it is embedding. Let us understand this embedding in more detail. In simple words, it is converting the text into numbers that is known as the vectors. Okay. So now what is a vector? A vector is just an order list of numbers. For example, here you can see 0.12 minus 0.35, 0.67, minus 0.21, and so on, whatever. But in practice, embedding models produces vectors with hundreds or even thousands of numbers. And this is nothing but hundreds of dimensions. So if you have a two-dimensional x coordinate, y coordinate, so this is not a two-dimensional, it is thousands of dimensional, high dimensional numeric representation. This is nothing but a vector, embedding vectors. Now, why we convert text to numbers? What does that buy us? This is the question which is worth really understanding, correct? So key insight here is the embedding model is trained in a very specific way. Text that means similar things get converted into vectors that are close to each other in this mathematical space basically. Okay. So let's say these are our three chunks. These three chunks, these are from our university documents. They are small text segments basically. Chunk 1, chunk 2, chunk 3. Okay. Now these particular three chunks using the embedding model, which will convert that particular text into vectors using the semantic meaning. Now these are getting converted into numbers. So this particular chunk or this particular text is now this particular vector. So vector 1, vector 2, vector 3. Okay. Now these vectors get stored in the something called as vector database. So in vector database, we have what vectors along with the original chunk text. So original chunk text and the particular vectors corresponding text and the corresponding number or vectors you have stored in the vector database. Now this vector database is nothing but a knowledge base. So in this particular diagram, you can see vector 1 and vector 2. Vector 1 is related to fee dates and vector 2 is related to late fees, which are close to each other in the vector space because they are both semantically related to fees. Vector 3 is about exam eligibility. So this is semantically far away from these both vectors. So vector 3 is far away in the this particular space. Correct? So this is nothing but this encodes meaning as a geometry basically. So the embedding model has learned that semester fee deadline and late fee applicable are semantically related concept. And it represents that the relationship as a closeness in the vector space. So this is what enables a semantic search. So when a user asks, when is the fee due? Even though the document doesn't say fee due, it says semester fee must be paid before. The query vector and the document vector are close to the vector space. So the retriever will find this particular thing. This is the fundamentally different from keyword search. So we are not matching the keywords. We are seeing the meaning basically. Okay. Now let us talk about the vector database. Now vector database is both a storage system and a search engine both. So it is built specifically for vectors. Now each row in the vector database has three things basically. Okay. In vector database, we have three things. One is chunk text. So here I can zoom and show you what does vector database have. We have a chunk text, we have the metadata or the source, and we have vectors. So chunk text is nothing but the actual original text. Metadata is that where it came from, like PDF name or the page number or the version, document version, whatever. And vector is nothing but the numerical embedding of that particular text or the chunk. So this is nothing but a knowledge base, potentially thousands or millions of rows like this, each one a searchable unit of knowledge. So this vector database will consist of this thousands or millions of chunks with the corresponding vectors or embeddings, correct? Now how this search happens? Let us try to understand how this search happens. Now this is a complete flow chart how vector database works or how the search happens in the vector database. First thing, user asks a question. What is the late date to pay semester fees? So this is a question asked by the user. Second thing is convert the query into vector. So that particular question goes to the embedding model and the result is a query vector. So that particular text gets converted into numbers or vectors. This is critical. You must use the same embedding model for both chunks and the queries. If you use different models, the vector space will not align. So basically, you have to use the same embedding model which you have used during the ingestion also and here also in the vector database. The vector database will receive that query vector basically and the vector database already contains vectors of chunks. So these many chunks are there, it will receive that particular chunk also, it will store in the vector database basically. Now, next step is similarity search. So the vector database which will receive the query vector, it will compare that particular query vector with each single stored vector and it will calculate something called as similarity search. Now there are three common methods for this particular calculation of scores. One is cosine similarity, then dot product and Euclidean distance. What is cosine similarity? Basically, it will measure the angle between the two vectors. Now, these many vectors you have, and here our query vector is this particular vector 0.021 minus 0.73. Now, this particular vector will be compared with all these vectors which we have in our vector database. And how we will compare, we will see the angle in the cosine similarity. We'll see the angle between the two vectors. A score of 1, it means they point exactly in the same direction, completely similar. If the score is 0, it means they are perpendicular, they are unrelated. A score of -1 means they point in opposite direction. So cosine similarity is most commonly used method in RAG because it handles the vectors of different magnitudes also. So it purely focuses on directions. It handles the vectors which represent the meaning. Okay. Then is a dot product. So what is a dot product? So basically multiply the corresponding elements of two vectors and sum them. It is basically faster than cosine similarity, but it can be influenced by magnitude of the vectors and not just by their directions. So it is used when vectors are normalized or basically all vectors have same magnitude, then we can use the dot product. And third thing is about the Euclidean distance. So this is the straight line geometric distance between the 2 points in the high dimensional space. Smaller distance means more similar, larger distance means they are not similar. So they are different. Right? So it's just like measuring how far 2 points are. Okay. So once the similarity search is took place, similarity calculations are done, similarity scores are found. So for each chunk, for that query vector, we'll compare it with chunk 1, chunk 2, chunk 3, and so on. And for each comparison, we'll get a similarity score, 0.94, 0.91, 0.87, like this. Now, the next thing is to return the results. So return the top k results. So the database returns the top k. If my value is 3, so it will return the top 3 results basically. Top 3 most similar chunks or most similar vectors. So here I have got 3 chunks, chunk 1, chunk 2, chunk 3 with the similarity score. Now important, what's come back from the database is the original text of those chunks and not the vectors. So what result we get is original text and the score basically. Or basically we get the original text and we don't get the vectors. So here we'll get the particular text, the chunks. Now vectors were just the search mechanism. The LLM will now work with the text. Correct? So these vectors, why we use these vectors? These vectors are basically used for searching the related information or meaningful information. Now, when we give this particular result to the LLM, we will give the text and not the numbers or not the vectors. Now, next step is send the retrieved chunks to the LLM. So the top 3 chunks get combined with the original question to prompt. So these particular 3 chunks we get, it will get combined. So the user query, what is the last date to pay semester fees, plus the relevant chunks combined together, we will go to, will send it to the LLM with an prompt also, correct? This is the question, this is the context, whatever it is. Now the LLM will generate us the final answer that the last date to pay the semester fees this particular date and the late fees become applicable from 1st July. And it will also give me the sources. Like I found this particular information from this particular PDF, page number 3, from this particular PDF, from this particular website, and whatever it is. So it will basically cite that particular information. Now these were complete step that how this vector database works or how this particular semantic search happens, similarity search happens, or how the results get retrieved. Now let us talk about a complete RAG pipeline. First is the ingestion, that is data sources, then extract, clean, split it into chunks, then embedding generation, then build the semantic index, organize the vectors in an index for fast similarity search, then store them in the vector database, and then the knowledge base is ready. Now we are going to use this same embedding model. Same embedding model is used when a user gives us a query. Then same embedding model converts that particular question to vectors, and that particular again is stored in the vector database, and now it is compared with all the vectors in the vector database or in the knowledge base, and then it will give me the top k results. Then we'll retrieve that chunks, then we'll give that particular chunks along with the question to the LLM. We'll prompt that LLM, and then LLM will generate an answer, and then we will get the final answer. So this is the complete RAG pipeline basically, correct? So I hope you understood about the complete RAG pipeline. So far, we have discussed about what is RAG, why we need RAG, then applications of RAG, then RAG phases, phase one, phase two. Then we have discussed in detail about each phase, and the complete RAG pipeline is in front of you. So we will go further. The last part of this video is about knowing about different RAG architectures. We are not going to learn about the architectures in detail, but we are going to see the overview about the architectures. So the different RAG architectures. So there are many RAG architectures. I have covered here the most important one. First one is the standard RAG. So this particular thing is nothing but that we just build a single vector search, which will retrieve the top k chunk, send it to LLM and generate the answer basically. So this standard RAG is nothing but the whatever pipeline that we have learned now. Okay. Let us go to the next architecture, that is hybrid RAG. What is this particular hybrid RAG architecture? Okay. So basically the standard RAG uses only semantic search, vector similarity. But semantic search alone is not always enough. Why? So let's say imagine a user searches for invoice or a legal clause reference like section 4.2b, anything. So semantic search, which works on meaning, might actually miss this particular exact specific matches because it's looking for conceptual similarity and not an exact string match. Correct? So what hybrid RAG does is this solves this by combining multiple retriever methods simultaneously. It has basically multiple methods, vector search. So it will use the embeddings and cosine similarity to find the meaning-based matches, which is great for tell me about the late fee policy. It will also have a keyword search, which is used for lexical analysis. So it will also find the exact word matches using the traditional information retrieval algorithms, TF-IDF, BM25, whatever it is, which is great for specific product codes or person names or document numbers or exact terms you have to match or not. Okay. Then we also have cross-encoder semantic rewriting. Now, what is this? Which is more deeper, basically more conceptually expensive model that will take the top results from the first two methods and it will rescore them for relevance. Then cross encoders basically will process the query and document together. So rather than independently, which gives us more accurate relevant scores, but it is slow, right? So to run on a full knowledge base, so it use a second pass re-ranker on the top k results. So this is what a cross encoder similarity does. Then before any retrieval happens, there is also an intelligent query processing. So there is something called as query rewrite, which will rephrase the user's query to be a clear and more searchable response. Like fees, if user has only given one word fees, so it will become what are the semester fee payment deadlines. So basically it will rephrase the user query. Then intent detection. Intent detection means understand what kind of answer the user wants. Does the user want a definition, or it wants a particular date, or it wants a particular procedure? What answer it wants? Query expansion. So it will also add related terms to improve the recall. Filter metadata. So it will apply a pre-filters based on the source type, date range, or department, or other metadata before the search rings. Okay. So all three retrieval methods run in parallel basically. Their results are combined and deduplicated using re-ranking and fusion algorithms. So there are algorithms like reciprocal rank fusion, which gives each result a combined score based on its rank across multiple retrieval methods. The best results from all methods comes to the top list. So what is the benefit of having this particular hybrid RAG is that accuracy increases. It is robust to the query variations. So it works whether you ask precisely or you don't ask precisely. It better coverage and recall. It improves your answer quality and is also adaptable to different use cases. So that's why it is basically best for enterprise search or research tools or any systems where user asks queries in many different ways and precision matters there. Okay. So these were complete overview about the hybrid RAGs. The next architecture is about the RAG with memory. RAG with memory means there is some conversational memory inside this particular RAG. So what is the fundamental limitation of standard RAG and the hybrid RAG is that every query is treated completely independent. If a user asks what are the refund policies for the international students, the system answers. Then the user asks next question, what about the students from India? Now the system does not have idea what about refers to. Basically, it has completely forgotten that the previous question. So basically, that particular system will not have idea about what you asked earlier. So RAG with conversation memory solves this by maintaining a conversation memory that is passed alongside the retrieve context on every query. So what are first if I ask like this, what are the refund policies for international students? Then the second question is what about for students from India? Then and is there any deadline to apply? Are there any deadlines to apply basically? So these are my four questions. Now basically what will happen? The system needs to understand that each follow-up question builds on what come before. So whenever I ask the second question about the refund policies, but specifically for the Indian students, so without the memory, the system will try to answer what about the students from India in isolation, which makes no sense, right? The conversation memory components has three distinct types basically. First is the short-term memory, recent terms. Okay, short-term memory, this is the recent terms. So it will store the recent messages of the conversation. Then summarization memory. So basically, as the conversation will grow further, and if the length of the particular conversation is beyond manageable length, older messages will get automatically summarized into a compact form. So instead of keeping a 30 old messages, you will keep a 5 sentences summary of that particular 30 messages like this. Facts, entities, memories, long-term retrieval memory basically. So these basically extract and store important facts, entities, and the user preferences. As the conversation will progress, important facts, etc., things will be extracted and stored persistently. Basically, if the user mentioned I am in the computer science program, so this particular fact gets stored and remembered for rest of the session. There is a memory retrieval. So fetches the relevant memory based on the current query and the intent. So for each turn, whatever is the question, it will fetch the relevant memory based on the current query and it will then further get processed. Okay, so this is all about the RAG with memory or conversational memory. Second, for next architecture is about a self-RAG. Self-RAG is nothing but standard RAG will generate an answer and immediately will return that particular answer. But why we require self-RAG? Self-RAG will generate answer and then it will ask itself, is this good enough? Is this answer actually supported by the evidence I retrieved? Can I make this answer better? Can I do better like this? So it is basically asking self to itself that is my answer generated correct or is it supported or is it good? Should I improve it like this? So here is a full flow. Step one is a retrieve. Okay. So retrieve the top tier relevant chunks from the vector database. That is standard retrieval, right? Then is a generation. So the LLM generates an initial answer. So here you can see the generation step. And then the third step which gets added here is a self-reflection. That is reflect and self-evaluate. So this is a unique step. The LLM now evaluates its own answers across the four quality dimensions. Basically soundness. Does the answer make retrieved context, logical sense? Soundness. Does the answer make logical sense? Groundedness. Is every claim in the answer actually supported by the context? Or is the model adding information that was not there in the evidence like this? Then completeness. Does the answer fully address all parts of the question? And the accuracy. Is the answer specific or facts correct based on what was retrieved? Like this, it will self-reflect all these answers. And the step four is about the decision. Now it will answer these questions. And if the answer is sufficient and well supported, that is yes, correct. So it will return up to the user, job done. If no, the answer failed evaluation. System goes back to the step one re-retrieval. So again, it will perform the particular steps. So it will retrieve the additional chunks if required. It will refine the search and it will try again. So this loop continues until the answer passes the particular evaluation. Now, why does this particular thing matter? Why we have self-RAG? So if you generate an answer that cites a document for a claim, but when you read more carefully, the document is not actually say that. So the LLM is basically extrapolated, right? So self-RAG catches this by explicitly checking that is your answer generated or is this claim actually in the evidence or not. So if it's not, that's a failure. Retrieve it again like this. Okay. So basically it is improving our accuracy of the answer. It is reducing the hallucination. The model actively checking if the claims are grounded or not. It is fetching more context only when needed. And it is better for complex and long tail queries basically. Right? So we use this for high accuracy, medical information system, legal document queries like this. Next RAG architecture is about agentic RAG architecture. Okay, now in this particular agentic RAG architecture, here the key new component here it is LLM agent orchestrator. Now what is this particular thing? Think of it like LLM not just answering, but it is planning or it is acting. The agent orchestrator. Now the agent does five things basically. It understands the query, it plans the step, it chooses the right tools, it decides what information to retrieve and iterates if needed. So So understanding the query makes it not just a surface level, but in terms of what information is actually needed to answer it. So it decides what sequence of actions will lead to the best answer. And also it forms a set of available tools. Pick the most appropriate tools at each step. And it will decide what information to retrieve and from where to retrieve like this. And it will also reflect on intermediate results if necessary or if needed and decides whether to continue gathering the information or generate the answer like this. Okay. So the agent has access to tool set, which is nothing but a collection of capabilities it can invoke. So basically the tool sets are nothing but vector database search, then web search, search for internet like SQL database, query structure data, student records or grades or registration data, things that live in tables and not the documents. Then it can also have API or external services, get the data from the APIs. So if you want a live data, current exchange rates or live weather or real-time inventory like this. Knowledge graph, search the interconnected entities and the relationship. So for complex multi-hop reasoning across the related concepts. So there. So look at this particular example reasoning for the question, what are the refund policies for international students? So the agent's internal reasoning will be, it will first search the university policy document. So it will call the vector database, correct? Now, the policy document has general information, but it might be outdated. So let me check the latest announcements. So it will call the web search website or another document sources. So I should verify from the student portal. So then it will call the vector database search on different collections basically. Now, if it has enough information from these three sources, it can generate the answer. Then it will call the LLM generation like this. So this is how it will work basically. Now, after each tool call, the agent goes through an observation iteration loop. So this is nothing but agent executes the selected tool basically. So after execution, the tool will return some results. That is nothing but my observation. The agent will analyze this particular observation or result and it will make questions. So do I need to use more tools or refine my query or generate the answer like this? So this loop repeats until the agent decides if it has a sufficient information or not. Once the sufficient information is there, once the information is gathered, it will generate basically the answers. Now this particular agentic RAG is based for complex workflows, autonomous AI assistants, like any system where a single vector search is insufficient, sorry, like this. So I hope you understood about this particular RAG architecture. Next is our graph RAG architecture. From the word itself, graph, that means here we have to make use of something called as graphs. So standard RAG is great at finding similar text, but there is a fundamental thing it cannot do is It doesn't understand the relationship between the things. And if my question is like this, which professor teaches the course that is prerequisite for machine learning? Prerequisite means, so it is going to find the machine learning course, and it will going to identify what the course list as its prerequisite. And then it will going to find the professor which teaches that particular prerequisite course, right? Now this is nothing but a chain of relationships. The standard vector search might find the individual pieces of this chain, but it cannot reason across the connections. So it can't traverse the relationship. So for that, you need multiple searches and manually connect the dots basically. That's where the graph rack comes in. So graph rack stores knowledge not in a flat vector database, but in a knowledge graph basically. So a database of entities, the things that exist and their relationship, the connection between the things. So here the phase one is about a knowledge graph. So what happens in the knowledge graph? We have the data sources, we extract and chunk it. So the information is extracted. The key step that is extract the entities, relationship, and key facts from the text. And then we build a knowledge graph. Okay. And then we store that particular in a graph database basically. So graph database, Neo4j, ArangoDB, Amazon Neptune, these are the some graph databases. Okay. Now the second phase is about query processing and answer generation. Now here what happens? User asks some query, which professor teaches the course that is a prerequisite of machine learning. Okay. Now basically the LLM understand the query and it will translate into a graph traversal strategy. So it will find basically the course where the name is machine learning. It will traverse each prerequisite of relationship, right? Now it will find some courses such as artificial intelligence or statistics, mathematics like this, whatever. And then it will traverse to the relationship of teachers, and then it will find the professor basically. So answer will be Professor ABC, whatever it is, teaches the particular prerequisite course, which is prerequisite for the machine learning. So this is how it will process basically. Now, why we require graph wrap? Basically, graph wrap will capture the relationship between entities. So it is not just semantic similarity of disconnected text passages. It is basically enabling us multi-hop reasoning, following a chains of relationships across the knowledge graph, and more accurate and far less hallucination for relationship-based questions, correct? It is explainable answers. It is going to be explainable answer with traceable paths through the graph, right? So basically, this is best for knowledge discovery or relationship-heavy domains, fraud detection, or any entity-linked question answering thing. So I hope you understood about the graph RAG. The next RAG architecture is about a multimodal RAG architecture. Multimodal RAG basically it will extend the entire RAG beyond text to handle any type of data. So it can handle text, it can handle images, it can handle audio, videos, diagrams, whatever. So the reality is the real world, in the real world, data is not just in the text. So let's say hospital, it has X-rays, images. It also has clinical notes. So as well as images, as well as text. Then a financial firm has both charts and graphs. A university database has diagrams, PDF textbooks, lecture recordings. So data in spreadsheets. So the data basically is in different formats, right? So standard RAG ignores everything that is not text. So what multimodal RAG handles is, so basically user can provide a text questions, images, tables, CSV, audio, voice, or documents like PDF. So it has basically tool sets, vector database search. So this is for a standard text retrieval. It has also image retrieval. So basically it will search for relevant images, diagrams, and screenshots. Then it has also has stable query engine. It will execute a query against a structured data in spreadsheets and the CSV files. Then it also has an audio transcription. It will basically convert your voice or audio recordings to text and extract that particular insights. Then multimodal embeddings. It will generate the embeddings for text, images, and audio all in same vector space. So this will enable cross-modal retrieval. So why we use multimodal RAG? So basically first is it understands all types of data. Nothing is invisible to the system. It is going to combine the strengths of the all multimodal modalities for more understanding of the data. It is going to answer the complex questions, real world queries. Okay. And it produces more accurate or context rich comprehensive answers. So basically, this particular RAG architecture is best suited for medical imaging, financial reports, then multimedia enterprise knowledge base like this. Okay. Now, which architecture to use basically? This completely depends upon the use cases, right? So if you use standard RAG, it is best for simple use case, basic Q&A and quick document search. Hybrid RAG, when you need better recall and precision, when user asks queries in different ways. Then RAG with conversation memory. So when you are building a chatbot or any conversational interface, so that time you can use this particular RAG architecture. Self-RAG when your accuracy is more critical, medical, legal, financial domains where Agentic RAG you can use when questions require multi-step reasoning across multiple sources. Graph RAG you can use when your domain has a rich relationship between the entities, when the questions require traversing connections like this. And multimodal RAG you can use when your data includes images also, audios also, tables or diagrams alongside like this. Now, what is the challenges in RAG? We'll discuss that. Challenges in RAG is data quality and preparation. This is the most common issue. So if your source documents are poorly formatted or if they contain errors or have inconsistent data or are structured in unusual ways. So of course your RAG system will foundation reflect that particular thing. So that's why investing in data quality is not optional, it is mandatory basically. So many RAG systems fail not because of the bad algorithms, but because of the bad data. Second thing is the retrieval accuracy. So getting the right chunks consistently is genuinely hard. So user ask ambiguous questions. So they use different vocabulary from your documents. A purely tuned retriever returns slightly wrong chunks. And then even a brilliant LLM cannot give a good answer because its starting material is wrong. So the retriever is often the actual weakest link in the chain. Third is the hallucination and reliability. So even with RAG, LLMs can still hallucinate, especially when the retrieved context doesn't fully cover the question or when the retrieved chunks are misleading. So the LLM might extrapolate beyond what the context says. So self-RAG and grounding strategies helps them significantly, but this is on ongoing engineering challenge basically. Next, the context window limitation, which we already discussed. You can only send a finite amount of text to the LLM. Scalability and performance as a knowledge base grows to millions of documents. So keeping that vector search fast and accurate is a challenge. Vector database use approximate nearest neighbor algorithms, that is ANN algorithms, right? Which trade small amounts of accuracy for huge speed gains at scale. But tuning this requires expertise and ongoing maintenance. Then is a data security. So your knowledge base contains sensitive information, personal data is there, property, business information, there are legal documents or medical records. Who can access which parts of knowledge base? How do you enforce a row level or document level access control in that? This is a very critical consideration in that. And the last part is the cost management. Every embedding call, whatever you will make, you will use an embedding model. The call you will make cost money, right? So every vector database query has a cost. Every LLM API call has a cost. At scale, millions of queries per day. This will cost add up to very fast. So catching frequently retrieved chunks, choosing appropriately sized models for each task, and batching the operations are also important cost management strategies. So these are the some challenges or while implementing the RAG also. Okay. So to have some quick recap, what we have learned today is we understood why LLMs are not enough. Then we understood what RAG is. Then we walked through every step of the pipeline of the RAG architecture. We explored the 7 RAG architectures and we also understood the challenges and when to use which RAG architecture. Okay. So if you made it to the end of this video, thank you so much for watching. Please like this video if you found it valuable. It tells YouTube to show this to more people who need it. Share it with someone who is getting into AI and subscribe to the channel because there is a lot more content like this on the way. Drop a comment, tell me which architecture you found most interesting, which one you will build first, and I will reply to every single comment. Thank you so much for watching. See you in the next one.